we are now going to talk about the derivative function, f prime of x. So far in this lesson, I have not once mentioned f prime of x. What we have mentioned is f prime of a. For an example, maybe we talked about f prime of 1, or maybe we talked about f prime of negative 3. And these are the derivative of a function at a particular x value, and each of them, provided that they exist, produces a real number. So a value, let's say perhaps the number is 7 or negative 3, a real number provided that the value exists. And it represents the slope of a function at a particular value. Now this f prime of x does not produce a number, but rather it produces a function. So you might say this produces a slope function. But the difference is function versus value. Now let's consider the example where f of x equals 3x squared minus 2. The goal here is to find not the derivative at a particular point, but the derivative function. So I'm using f prime of x. And so we're going to use this definition, and this definition is probably what you used if you used a definition similar to this in a prior course. You said the limit as h goes to 0 of f prime of x plus h. So far in this course, we have never said that. We said 1 plus h or negative 3 plus h. Okay, but this is the one you've probably seen before. And so we go through this process, the limit as h goes to 0. The algebra is the same. Here we're going to have 3 times x plus h quantity squared minus 2. And then the function itself is 3x squared minus 2. There is no alternate definition when we're finding the derivative function f prime of x. There's only the standard. Okay, so I'm just going to work through the algebra, even though this should be fairly straightforward if you've been following along in all the lessons. 3x squared plus 6xh plus 3h squared minus 3x squared. I've gotten rid of the constants already. Okay, all over h. And so we simplify further still. The limit as h goes to 0, factor on to h, 6x plus 3h all over h. Keep it going. Limit as h goes to 0 of 6x plus 3h. I'm now able to substitute 0 in for h, and we get 6x. So f prime of x is the function 6x. This is a slope function. It tells you what the slope will be at varying points of x. In part B, when it asks for equation of a tangent line at both x equals negative 1 and x equals 5, we're going to run through a similar process. F of negative 1 is computed to be 1, and then f prime at negative 1, well, we'll use our slope function, so 6 times negative 1, which is negative 6, and that leads to the equation y minus 1 equals negative 6 times the quantity x plus 1. Similarly, f of 5, when we're writing this equation, well, that's going to be 73. F prime at 5, we'll use the slope function, 6 times 5 equals 30, and so we have y minus 73 equals 30 times the quantity x minus 5. It all depends what we're trying to find. If the only thing you're asked to find is f prime of x, then you are asked to find this slope function, and then you leave it alone. Beyond that, you may be asked to write an equation of a tangent line or ask what is the slope at a particular x value, in which case you have to do some substitution or some additional math. In part C, it simply wants the equation of the normal, so we'll review that. Y minus 1 equals, if you recall, we need the negative reciprocal, so 1/6 x plus 1. That would be the normal going through the same point as this equation up here. This one was the tangent line, this one was the normal line. And for the other one, we have y minus 73 equals, negative reciprocal here would be negative 1 over 30. and x minus 5. Next, we want to find the points on f of x where the slope is parallel, or the tangent line is parallel to this line. So the important information we take from this line would be its slope. So we know that this line has a slope of 4, which means f prime of x has to equal 4. The slope, which is f prime of x, so f prime of x, which is the slope, that has to also equal 4. We have to figure out where that's going to happen. And of course, the slope function is 6x, and we want to see where that equals 4. So clearly, it's going to be when x equals 2/3. That's the x value where we're going to have the phenomenon that the tangent is parallel to this line. It's not going to be the same as that line. It's just going to be parallel. And to find the actual ordered pair, we have to find f of 2/3, which equals negative 2/3. And so the ordered pair would be 2/3, comma, negative 2/3. We are next going to graph a derivative function. The function to the left is g of x, y equals g of x. And the function to the right will be this function, y equals g prime of x. It's important to remember what the function will represent to make most sense of it. The g prime of x will be a picture or a graph of the derivative for each point. So to just illustrate this, if I come over here and say, what is the slope of our function g? What is our slope at negative 3? We would say that that slope is equal to 1. And so I could plot a point at 1. If I ask, what is the slope at negative 1? Well, I would just do a little rise over run, and let's see, rise, run. So that's going to be negative 2. So at negative 1, the slope would be negative 2. The picture to the right tells us what the slope will be. How about at 1/2? At 1/2, looks like we have a slope of 3. At 2, we have a slope of negative 1. Are you following me? At 2, the rise, run, slope would be negative 1. So it looks like for all points between negative 4 and 2, for all these points, the slope is always going to be 1. So between negative 4 and 2, the slope is always 1. And I'm purposely being a little ambiguous at negative 2 exactly. And then the slope jumps. The slope is going to jump to this, which we said was negative 2. So between negative 2 and 0, the slope jumped to negative 2. All right. And then the slope jumps up to 3 for between 0 and 1. And then the slope jumps again to negative 1 for between 1 and 4. All right. So there we go. Now I want to discuss what is the slope at negative 2. Well, if you've been following along, you realize there is no slope at negative 2. So our picture, our graph, has to represent that. So we need an open circle at negative 2, so that if one were reading this graph and you ask that person, what is the slope at negative 2, they would say, it's undefined. There's no point on my slope graph because there is no slope on our original graph. And that concept is going to be true for all the corners. So here we have an open circle, and at 1 we have an open circle. Good. Now the question becomes, what happens at this endpoint? So you'll notice that this endpoint is solid, and because the endpoint is solid, and because the slope comes in from the direction, from one direction, we say that that point will take on the slope. And so it does have a slope at negative 4, so I'm going to fill in the circle. Again, the reader comes over and says, what is the slope at negative 4? The slope is 1, and that's consistent with our graph. The slope at that point is considered 1. And same thing goes for the right endpoint. This endpoint is defined, and the slope is approaching negative 1, so we will have a closed circle. In the event that this picture over here, let's say this originally had an open circle, well, since it's not defined, we can't have a derivative, in which case we would have an open circle. But again, these are both closed. Endpoints are both closed because we have closed circles and the respective one-sided derivative exists. In just moments, we're going to give an accurate graph of a function that has this as its derivative. You can see from this that the slope is going to jump. The slope is going to be -1, and then the slope will jump to 0, and then the slope will jump to 3. So before we get into the nitty-gritty details, I want you to have the general shape of this. The slope is going to be -1, and then the slope is going to be 0, and then the slope is going to be 3, so steeper. So this is a candidate for such a graph that has that quality of the slope jumping in the directions that I have presented in my formula, my slope formula. So this graph here is a candidate for what this could look like, or perhaps it's going to go slope of -1, I'll put an open circle, and then a slope of 0, open circle, and then a slope of 3. Again, that's going to be steep. So perhaps our function will look like this. So let's say the slope went like this, and then it jumped to 0, and then it jumped to 3. So this graph here is yet another candidate. So there needs to be more information for us to be able to graph this appropriately. So I'm going to come down here, and hopefully this will be the real graph that we desire. Okay. Cool. Now, let's graph a function that has this as its slope, like we've done over here. The one piece of information that we're first going to highlight is that f of -1 equals -2. We know that the function has to pass through that point, so at -1, the function's value will be -2. We know we have to have a solid point here. Now, to the left of -1, we know the slope has to be -1. I also want to point out that the domain of this is going to go -3 to 1, 2, 3. That's why I've put these circles here, because I knew the domain was going to cut us off. Okay, so the way I'm going to draw this is at -3, we say the slope will be -1. So it goes like this. So see how the slope is always -1 on that interval. And then the slope is going to jump to 0. Okay, and that's going to be all the way up to 2. I'm going to put an open circle here. And now the slope has to jump to 3. So up 1, 2, 3 over 1. Okay, so I'm going to draw it like this. Maybe this is right, maybe it's not right. That's what I want to talk about. So this was one graph that the slopes changed in the way it needed to. This was another graph, and this was yet another graph. So in the way that I've drawn it, I have them connected. Is this the right graph? I want you to, hopefully in your mind, you're right now just saying, you're missing something. And the thing that I'm missing, and I don't want to do it yet, but I need to eventually fill in that hole here. Why do I need to fill in that hole? Well, the information at the top told us that f is continuous on -3 to 3, which means f is continuous for every point inside -3. If I leave this open hole here, well, then I do not have that quality. I have a discontinuity, but it has to be continuous everywhere. So what I need to do, and I'm just going to pick a different color, I'm going to fill in that hole. Now we have the quality that we want. This is now continuous for every point between -3 and 3. Good. And it has the quality that the slope goes -1 to 0 to 3. Now some people also ask, how come there are no equals in these inequalities above? None of them are equal. That's because we have corners, and when you have a corner, the derivative doesn't exist, so I certainly can't say equals, because then that would imply that the derivative has a value when it equals -1, 2, etc. So finally, if I did not have this information here that f was continuous, then this would have worked. That certainly would have been a correct function. This would have been a correct function. So would have this. Of course, provided that they all had this quality here. But the only reason we know that they're connected is because of the continuity feature.